Hey, what's up, everyone, and welcome. We all know that little Wi-Fi symbol, right? It's our magic portal to pretty much everything. But, when that connection drops or your video starts buffering for the 10th time, it feels a whole lot less like magic and a lot more like a total mystery. So today, we are going to pull back the curtain and really understand what Wi-Fi is, why it can be so dang frustrating, and what the future has in store for it. I mean, this is the ultimate question, isn't it? You're paying for that blazing fast gigabit internet, but the second you try to stream something from the couch, it feels like you're back in the Stone Age. You run a speed test right next to the router, the numbers look amazing, but your actual experience, well, it tells a very different story. So what's really going on here? The key to solving this whole puzzle is actually surprisingly simple. At its very core, Wi-Fi was designed to be a direct, wireless version of that good old Ethernet cable, the one you plug into your computer. It's not some magical cloud of data. You have to think of it as a wire, just without the actual physical wire. And once you really let that sink in, that Wi-Fi is just trying its best to be an Ethernet cable, all of its weird quirks and all of our frustrations suddenly start to make a whole lot of sense. Okay, so here's the game plan for today. First, we're going to break down what Wi-Fi really is. Then we'll get into the very polite and sometimes slow rules that govern the airwaves. After that, we'll take a look at its evolution in speed, switch gears to a super practical playbook for developers, and finally, we'll get that senior level upgrade by diving into the latest and greatest Wi-Fi 6 and 7. All right, let's get down to the fundamentals. The technical name for Wi-Fi is IEEE 802.11, and Ethernet is 802.3. Now, those names are deliberately similar because for all intents and purposes, they're siblings. They were born from the exact same networking principles. And to see just how close they are, we gotta look at how network communication is structured. Now, check this out. Think of these network layers like departments in a big company. Way down at the bottom, the physical layer is the mailroom. It just moves raw bits around, either through a copper wire or through radio waves. Now that green section, the data link layer, that's like the company's internal mail service. It puts data into envelopes, which we call frames, and makes sure they get to the right desk inside the building. And look, as you can see, both Ethernet and Wi-Fi use the exact same data link layer. They speak the same language. The only thing that's different is the mailroom, the physical medium. And that one single difference is the source of all of Wi-Fi's strengths and pretty much all of its weaknesses. So because Wi-Fi doesn't have a nice, dedicated wire for every single device, it has to find a way to share one single invisible resource, the air itself. And this requires a completely different set of rules for communication. Okay, this is the crucial difference right here. Ethernet is aggressive. It uses something called collision detection. It basically just starts talking, and if it hears someone else talking over it, it stops and tries again later. But Wi-Fi can't do that. Think about it. A radio's transmitter is like a giant speaker, and its receiver is like a super sensitive microphone. If you tried to shout and listen for a whisper at the exact same time, you just deafen yourself with your own voice. So Wi-Fi has to use collision avoidance. It has to be way more cautious. It listens first, and only if the coast is clear does it even try to speak. And this brings us to this constant little conversation that Wi-Fi is always having. First, your device listens. If the channel's free, it sends out a little chunk of data. But here's the thing. It doesn't just assume it got there. It has to wait for the device on the other end to send back a tiny message that says ACK, which just stands for acknowledge. If it doesn't get that ACK back, it assumes the data got lost in transit, waits a random amount of time, and then starts the whole process over again. This constant listen-send-wait cycle is what we call overhead. It's all this extra chatter that has to happen just to manage the conversation. And it's precisely why Wi-Fi feels so chatty and is so prone to those random delays we feel as lag. But of course, Wi-Fi hasn't just been sitting still. To try and overcome these built-in limitations, engineers have been pushing the technology forward like crazy, and that's led to this massive evolution in speed and what it's capable of. Let's just take a quick trip down memory lane. We started back in 1999 with 802.11b, chugging along at 11 megabits per second. Then G came along with a nice little bump. But the real game changer was 802.11n. It introduced using multiple antennas and, most importantly, the 5 gigahertz frequency band. Then AC pushed things even further, making gigabit speeds a theoretical reality. But here's the catch. All this focus on raw speed was hiding a bigger problem. As Wi-Fi got more and more popular, the airwaves themselves were getting incredibly crowded, especially that original 2.4 gigahertz band. And wow, this image just says it all, doesn't it? This is what we call the cocktail party effect. Just look at the left side there. That's the 2.4 gigahertz band in a typical apartment building. It is a complete and utter mess. Every one of those colored blobs is a different Wi-Fi network, and they are all yelling over each other. Now look at the right side. That's the 5 gigahertz band. It's practically empty. It's the difference between a chaotic party and a quiet library. So why is it so chaotic? Well, the reason is actually pretty simple. The entire 2.4 gigahertz band only has 3 channels that don't overlap with each other. Channels 1, 6, and 11. That's it, just 3. So if you, your upstairs neighbor, and your neighbor next door all have your routers set to channel 6, you're not just near each other. You are literally on the exact same digital highway, all competing for the exact same space. And because of those polite listen before speaking rules, your router has to wait for their devices to finish their entire conversation before yours can even begin. And here is the cold, hard data to prove it. This table shows latency, which is just a fancy word for delay, for just that very first jump from a laptop to the router. On that nice, clean 5 gigahertz band, the typical delay is less than 1 millisecond. That is incredibly fast. But look at the crowded 2.4 gigahertz band. 5% of the time, the delay shoots up to nearly 35 milliseconds, and 1% of the time, it's almost 60. And just for some context, a single frame in a 60 frames per second video game is only 16 milliseconds long. This is a massive, noticeable lag, and it's happening before your data even leaves your house. Okay, so knowing all this, the chattiness, the interference, the wild swings in performance, how should we, as software developers, build apps that actually work well in the real world of Wi-Fi? You just can't assume the network is perfect. You have to build for chaos. So the playbook really boils down to 3 main strategies. First, leverage unmetered bandwidth. This is all about being a good citizen for your user's data plan. People often have caps on their cell data, but not on Wi-Fi, so your app should be smart and prompt them to do those big downloads or updates when they're on a free connection. Second, you have to adapt to variable bandwidth. Don't just measure the speed once and call it a day. The speed can plummet in a split second if someone in the next room starts streaming a 4K movie. And third, adapt to variable latency. You have to expect and handle those random delays, or jitter, gracefully. This is absolutely crucial for real-time apps like gaming or video calls, where one sudden lag spike can completely ruin the experience. And if you want to see this in action, look no further than the master of this, Netflix. This quote is just incredible. They don't have a low, medium, and high-quality version of a movie. They have over 120 different versions. This lets their video player seamlessly switch to the perfect stream that matches not just your screen size, but your network's real-time condition. That's why your movie might look a little fuzzy for a second, but then it snaps into crystal clear HD as soon as the player confirms your network can handle the load. It's genius. And you can actually put this kind of thinking into your own web apps. A lot of developers just check if a user is online, but that's not nearly enough. Being online doesn't tell you if the connection is any good. A much better tool is the Network Information API. This little code snippet here checks the effective connection type. It's asking the browser, hey, based on the real-world speed and delay you're seeing right now, does this connection behave like a fast 4G connection? A great Wi-Fi connection will report as 4G, but a terrible, crowded coffee shop Wi-Fi might report as 3G or even 2G. This lets you make smart decisions, like loading all those beautiful high-res images on a good connection, but maybe defaulting to just text or lower-quality stuff on a bad one. All right, time to level up for the Senior Engineer Upgrade. All of these problems we've been talking about, the interference, the inefficiency, the latency, they haven't gone unnoticed. In fact, the latest Wi-Fi standards, Wi-Fi 6 and now Wi-Fi 7, were designed from the ground up to solve these exact problems. The absolute biggest revolution in Wi-Fi 6 is a technology called OFDMA. And this analogy is perfect. With older Wi-Fi, if your phone needed to send one tiny little text message, a whole delivery truck was sent just for that one small package. It was incredibly inefficient. But with Wi-Fi 6 and OFDMA, a single truck can carry packages from multiple different devices all at once. This is a total game changer, especially in crowded places with lots of small data packets flying around. Think of a smart home with dozens of devices all trying to talk at once. Hey, remember our crazy, crowded cocktail party problem? Well, BSS coloring is the solution. It lets your router digitally color all the data from your network. Let's say it colors it blue. So now, when it hears data from your neighbor's network, which might be colored red, it can instantly recognize, hey, that's not my conversation, and it can just ignore it instead of politely waiting for the channel to be clear. This is a huge deal for cutting down interference in apartments and dense neighborhoods. Another brilliant feature in Wi-Fi 6 is target wake time, or TWT. This one is for all those little battery-powered smart devices in our homes. Instead of constantly staying awake and listening for instructions, a device like a smart lock can basically tell the router, hey, wake me up in 8 hours so I can check in. The device can then go into a super deep sleep, which saves a massive amount of battery life. And that brings us to the future, which is basically here with Wi-Fi 7. Its absolute killer feature is called multi-link operation, or MLO. This is the holy grail we've been waiting for. Your phone or your laptop can connect to the 2.4, the 5, and the brand new 6 GHz bands all at the same time. It's like having 3 separate highways to your router, and your device can dynamically send data down whichever lane is least congested at that exact millisecond. If the 5 GHz band suddenly gets noisy, it can instantly shift critical traffic to another band without you ever noticing. This delivers a level of reliability and low latency that until now was only really possible with a physical wire.
Which brings us right back to where we started, with this idea of wireless Ethernet. For decades, that physical Ethernet cable has been the gold standard for pure speed and rock-solid reliability. But with new technologies like MLO in Wi-Fi 7, which can literally bond multiple radio channels into one super robust connection, we have to ask the question, is the physical network cable finally truly on its way out? Something to think about. Thanks for watching.